everyone. This is Volts for September 25th, 2024. A new way to retrofit old buildings from the outside. I'm your host, David Roberts. One of the biggest and most difficult problems in building decarbonization is what to do about old multifamily residences, anywhere from 4 stories to a few dozen, that are poorly insulated, expensive to heat and cool, and uncomfortable to inhabit. Most retrofits, especially anything that would even approach zero emissions, are prohibitively expensive for the owners of these buildings, not to mention invasive, especially if, say, heat pump mini-splits must be installed in every residence. But what if you could insulate a building, dramatically reducing its energy demand, and update its HVAC systems, dramatically reducing its emissions, all without messing around inside it at all? That is what a New York City startup called Hydronic Shell Technologies is doing. It begins with attaching a new facade to the exterior of the building in the form of standardized, insulated facade panels. Think of them like Legos or Tetris pieces. They fit together snugly to create an airtight seal around the building, in the process replacing flimsy old windows with hyper-efficient new ones. Insulated facade panels are not new. They were pioneered in the Netherlands years ago. What's new is Hydronic Shell is embedding HVAC components into the panels so that the facade itself becomes the distribution system for central heat pumps connected to individual window units. It's called Facade Integrated Mechanical Systems, or FIMS, for those of you who love new acronyms. There's a lot more to say about this clever idea, but I have David Goldstein, the engineer who developed the technology and founded the company, with me, so I'm going to let him tell it. With no further ado, David Goldstein, welcome to Volts. Thank you for coming.
Thank you so much for having me.
David, I have to say just up front, reading about this technology really tickled my, whatever you call it, my geek funny bone. It's very pleasing. I have no idea if it's going to work as a business strategy, but just conceptually, it's just very satisfying, I have to say. So before we jump into it, let's move back a little bit and talk just for 2 or 3 minutes about what is the problem that this is attempting to solve? What is the problem that these FIMS are meant to solve? Let's talk just a little bit about what kind of buildings we're talking about and their current state and sort of like the other retrofit alternatives on the table.
Yeah, well, as a fellow geek, I'm excited to have this conversation with you because I'm equally excited by it. So let's start zoomed way out. And I'm sure you and many of your listeners know this, but buildings are obviously a huge contributor to greenhouse gas emissions. Mm-hmm. And, something like 40% of global emissions come from buildings. So we have a huge challenge ahead of us with the number of existing buildings that need to be retrofit. We have all these net zero targets, net zero by 2050, but that's going to require a huge amount of these retrofits in a very short period of time. And so our focus is on multifamily buildings, especially old multifamily buildings. These tend to be some of the largest emitters just because of their age and their poor condition. So many of them built without any insulation. They're very leaky, and they tend to have these old boiler systems, distributing steam or hot water throughout the building, and that's very inefficient as well. So these buildings have really high emissions, and not only does that make them so important, they're also extremely challenging because they need all this significant work to be done in order to decarbonize them. But people live in them. And that's really the crux of the challenge. I mean, you explained it well in your intro, but doing construction in an empty space is one thing. But when you try to do construction in an occupied space, and not just an occupied space, but someone's home, people's living rooms, people's bedrooms, it becomes a much bigger challenge, especially for multifamily. Like if you think of single family homes, for example, if someone wants to do a retrofit, when they start with that retrofit, the homeowner is on board. It was their decision to retrofit their home.
Yes.
But if you're talking about a multifamily building with 100 people in it or 100 families, they're not necessarily all on board. And they don't have an opportunity to meet the contractors and choose which one they want. To them, it's just a random contractor coming into their home to do work. And so this, creates a really challenging logistical situation, which is not good for the people who live in the buildings. It's not good for the contractors. The contractors don't like to be working in that kind of situation. And it's definitely not good for the building owners because it makes the work much more expensive, makes it take much longer, and it just makes it a lot riskier. You end up with a lot more unknowns associated with the project. And so the whole idea of what we're doing is to kind of eliminate that major challenge, as you said, by doing the work on the exterior.
If I'm the owner of, a 10-story multifamily residence, and I'm looking to do, I want to, I take New York City's new regulations to heart, and I want to go zero emissions. What's on the table now? Like, what will people do for me now? Like, what is the sort of standard go-to if I'm geared up to do it?
Well, that's a really good question.
Is there even an answer? Is there a standard?
Exactly. There kind of is no standard go-to. That's something I would say the industry is trying to figure out right now.
Yeah.
If you talk about old multifamily buildings undergoing deep energy retrofits and decarbonizing, how many of those projects have actually been done?
Yeah.
I don't know the exact number, but, it's a small handful.
And so many left to do, as you say, yes, in such a short period of time. Yeah, this is really one of the thorniest. People talk about difficult to decarbonize sectors. I've always thought that buildings should be first on that list, just because, as you say, it's like a logistical problem and just a mechanical, physical problem and an economic problem, because these are not necessarily wealthy people who own these buildings. They don't have a ton of spare capital laying around. So then let's talk about your alternative then. So there are 4 basic components to your system, and I kind of want to walk through them all one by one. But just to list them, there's the central equipment, which is, producing the heat or cooling, which I think is most often going to be a heat pump, but theoretically could be anything that creates heat and cooling. Like what are the alternatives here for the sort of central unit?
Yeah, in an ideal scenario, and I would say the vast majority of the time, it will be a heat pump.
Right.
But it's sort of agnostic to what the source is in terms of the functionality of the system. So, theoretically, and these are just some random examples, but, if a building owner has a new boiler that they just installed and they don't want to get rid of it yet, maybe you'll hook the system up to that new boiler, right, for the time being until the end of that boiler's life, and then you'll put in a heat pump.
Or a ground source heat pump, presumably you could.
Well, yes. So ground source heat pump is definitely an option. And I hope to do a lot of those. Yeah.
Or I guess if you're really lucky, there'll be some sort of district heating or centralized, network to hook into. And you could do that too, right? Like basically roughly agnostic to the source of the heat and cooling.
Yeah, exactly. Especially in a dense urban environment where you have, a lot of these big multi-family buildings packed together. The idea of doing a district thermal kind of network is extremely attractive.
Yeah, we're extremely into that here on Volts. Okay, well, let me just get to the list real quick. So there's the central equipment, there's the ducts and pipes that lead down or up from the central equipment to these, you call them terminal units, little heating, cooling units in the windows. And then there's the facade panels that are covering the ducts and pipes and the terminal units. So that's the 4 pieces. We're going to go through them one at a time. Central equipment, as you say, could be a heat pump, could be a boiler, could be anything really. Could be located on the roof of the building, could be located in the basement of the building or anywhere else. Can it be inside the building, or do you almost always want it outside the building somewhere?
It certainly can be inside. The example you gave of a geothermal heat pump, in that situation, you're probably want that geothermal water coming into the cellar of the building.
Right.
And then you can have your water-to-water heat pump in the cellar.
Talk a little bit about your decision, like say for, I don't know, like a 12-story building or whatever. You're not just trying to install one giant heat pump to cover all the units. You're doing this zone thing. Talk a little bit about that.
So, when you look at heat pump options, there's like kind of two ends of the spectrum. You can have unitary heat pumps, which is kind of one extreme where you actually have one little heat pump in every room of the building. Or you can go to the other extreme and have one big heat pump serving the entire building. There's, pros and cons of each one, but the way we approach it is to kind of find the sweet spot kind of between the two. So it is a central system, but it doesn't necessarily make sense to have one big central system. If you think about a building with a large footprint, certainly for at least a significant part, we'll be looking at large buildings. If you were to put one large heat pump, say, in the center of the roof, it becomes a very big, heavy heat pump that requires a lot of structural support to support it. But then you end up with a lot of distribution piping to get all the hot water and chilled water from that heat pump to all ends.
Loud too, yeah?
Yeah, exactly. More complicated to operate and maintain, a very large unit like that. So the idea is we're not at like large commercial size equipment. We're more like a light commercial kind of size equipment. It's equipment that's easy. You could fit it in an elevator and, lift it up to the top of the building in an elevator. You don't need a huge amount of structural support to support it on the roof. It's not necessarily visible from the street. You don't have this, giant thing sitting on the roof that's an eyesore from the street. And again, it just makes the distribution simpler because you're not distributing all
and
from one
quieter
source.
Too.
Yes, and definitely
not
quieter.
to obsess over the noise issue here, but I'm going to bring it up repeatedly. Like it's quieter. So you have these like zones where you'll have a sort of smaller heat pump that serves, I don't know, like how many. I mean, I don't know if there's a rule of thumb, but just like how many sort of apartments are you going to hook up to an individual heat pump?
Yeah, so it's one of those things, one of the challenges with buildings is that every building is unique and there's kind of no one size fits all. So it'll really depend a lot on the specific building and the height of the building in particular. But, one of the beautiful things about taking an approach where you not just install heat pumps, but also insulate the building and air seal the building is you can actually get the heating and cooling loads very low in the space. So you don't need a large heat pump to heat, a large number of apartments. So kind of the layouts we're working on right now, just to give you a sense, I would say one heat pump on the roof might serve 14 to 25 apartments. Could be more than that if you're dealing with a taller building, but I would say, in that sort of range.
So a really big building, you could end up with, 3, 4 of these on the roof, theoretically.
Yeah, exactly.
Okay, another question while we're talking about the central thing, you have these zones. Just conceptually, do you need to cover the entire building? Like you don't get the insulation and the air sealing unless you're completely wrapping the building, right? Like you couldn't do this in just one zone. You sort of need the complete wrap, do you not?
Well, to your point about zoning the central equipment, I mean, theoretically, maybe even more than just theoretically, practically, let's say you have a building with 4 wings, you have like an X-shaped building with 4 wings. You could do one wing of the building. You insulate that one wing of the building and put your central equipment on the roof to serve that one wing of the building. And you don't necessarily have to do the other wings. I mean, obviously, the intent would be to do a whole building, but if, maybe for financial reasons, the project needed to be phased, it's certainly possible to do an approach like that where you do kind of one portion at a time.
So you can still get a decent air seal if your facade is sort of running up against building at one end of it and not another facade panel, if that makes sense.
Yeah, it's one of those details, that you have to look at and make sure you do carefully. You have to make sure wherever that interface is between the retrofitted and the non-retrofitted portion, you probably want to take extra care to make sure it's properly sealed, but it should be doable.
Okay, so a couple of heat pumps up on the roof, not unfamiliar. So coming down from those heat pumps to individual window units, and we'll discuss the individual units in a minute, are Pipes and ducts. Explain what they're doing and what they're carrying.
Yes. So the pipes are doing heating and cooling to the space. So they're carrying hot water if the system is in heating mode, and they're carrying chilled water if the system is in cooling mode.
Not refrigerants, which is a little bit of a hassle when it comes to normal heat pumps, right? This is all water.
Exactly, and that's an important point. Refrigerants are fine for some applications, but as there's certainly issues with refrigerants, whether it's, environmental issues, safety issues around flammability, things like that. In general, there can be issues when you have refrigerants, especially in larger quantities. And so when you get to bigger buildings where you have bigger systems with longer distribution lengths, you're not just distributing 20 feet from an outdoor to an indoor unit, but, if it's a 100-foot tall building, you have much more distribution. So you're talking about much larger quantities of refrigerant. So using refrigerant becomes more and more of a problem.
Right.
So especially for larger buildings, water really becomes a much more effective way to move the heat around the building.
Right. So you have pipes carrying heated and cooled water. And what are the ducts doing?
And so the ducts are addressing the ventilation needs of the building. And so, it's important to talk about that a bit because, we're talking about electrification, decarbonization, heat pumps, but it turns out ventilation is actually an extremely important kind of part of the larger puzzle.
Yeah, I should have mentioned that in my intro, actually, especially if you're going to wrap an air sealing around the entire building. We had an episode on Passive House standards a few weeks ago and sort of learned about this. Like, if you're going to insulate the whole building with an air seal, obviously getting fresh air into it becomes much more important.
Yep, exactly right. I mean, even with the leaky buildings we have today, these older, often neglected multifamily buildings already have big indoor air quality problems.
Yeah.
This was one of the things, I really kind of opened my eyes when I had my first experience working on a project like that in one of those buildings. But it really is, I would say, a huge public health emergency.
Totally.
That people are, just forced to breathe really poor air quality, day and night. And there's nothing they can really do about it. And like you said, as soon as you seal that building, the problem is only going to get much, much worse. So really, we can't do this kind of work without addressing the ventilation needs of the building as well. And so part of the way our system works is that we provide a complete ventilation system. So that includes ventilation air, so that's outside air that gets treated by a central ventilation unit. So it's filtering the air, it's tempering the air, so heating it in the winter, cooling it in the summer, and it's also dehumidifying the air. And we're distributing this fully conditioned air down that distribution within the facade so that it can be supplied to every living room and every bedroom in the building.
So the same window unit that we're going to talk about in a minute is bringing the heat, bringing the cool, and bringing the fresh air. The same unit is the source of all those things.
That's right. So we have that distribution, the ductwork and the piping running in the facade. And the terminal unit is essentially plugging into that distribution network. So at the window, you have this terminal unit that plugs into the piping and it plugs into that ductwork to be able to deliver that heating, cooling, and ventilation into the space.
Yeah, this is an area where I feel like the audio nature of this medium is a disadvantage. It's very helpful to look at a picture of this. So you have these facade panels that you're basically hanging on the front of the building. And so just for listeners' benefit, you can imagine there's a facade and then there's the original facade of the building and there's a little gap between them, basically. And that gap is where all the ductwork and piping goes. So I'm guessing you are either buying or making your own extremely narrow piping and ducting. I mean, what do you have, like 6 inches there to work with?
That's right, 6 inches. And so fortunately, the ducting and piping is all very standard components that, you can get at any HVAC shop that any contractor is familiar with. Sheet metal duct, galvanized sheet metal, we'll have it, depth of it being anywhere from 4 to 5 inches so that it can fit within that 6-inch cavity. And that's standard ductwork, in the industry. And then the piping Piping is also quite small. Again, the loads in the building are very low. So that means you don't need a lot of hot water and chilled water to the spaces.
Yeah, this is worth emphasizing again and again. I just want to say it one more time. Like, if you are insulating the whole outside of the building as part of this process, you're just dramatically reducing the need for both heat and cool. So you can have smaller equipment.
Right. And on a conceptual level, that's key to making this whole system possible.
Right.
If you're going to jam a whole HVAC system into a little cavity in the facade of a building, you can't do it unless the loads are very low.
Right.
So the two really work together.
Right. So you have this narrow ducting and piping that's coming down behind the facade and hooking up to this terminal unit. So people can think of sort of the window in the original apartment gets popped out. You put this facade over the top of it that's got this newer, better window in it. So in the little gap between where the old window was and where the new window is, that's where this little terminal unit fits in. And I guess from the resident's perspective, you sort of walk over to your window, look down at the windowsill, and there's like a grate, basically. That's what the unit looks like to the resident, is basically a grate underneath the window. Yeah, so let's talk about these terminal units. Like, what are they doing? What's on them? What do they look like? How do you interact with them?
Yes, so the terminal unit is a relatively simple device in terms of what it's doing. There's very few components actually in the unit. In the industry, we call these units fan coil units. And the reason we call it that is because that's exactly what's in it. There's a fan and there's a coil. So I mentioned that you have hot water and chilled water coming to this unit. So that hot and chilled water runs through a coil, which is like a finned metal heat exchanger that you see on, kind of any AC unit, either an outdoor unit or an indoor unit, very common in the HVAC world. So it's that coil. And then you have the fan sitting right next to the coil that's circulating the air over the coil. So if you're heating the space, you have hot water running through that coil, and then the fan is circulating the air over that coil so that the air will get warmed up by that hot water. And so the air comes in from the space, runs over that coil, gets heated up, and then gets blown back into the room. So it's recirculating the air.
And I'm guessing these fans in the terminal units are relatively quiet.
Yes, exactly. So, one of the good things about having a unit that one has no compressor, because usually, with HVAC systems, it's the compressor that's creating the noise. So with a central system, the compressor is up in the central unit.
Right.
So in the actual terminal unit in the room, the only moving part is that fan.
Got it.
And because there's no ductwork, there's no real resistance to the airflow. It's not like you're pushing air through, an elaborate snake of ductwork. There's very little resistance to airflow. So the fan doesn't need a lot of power. It doesn't need to generate a lot of pressure to circulate the air. So it ends up being a very quiet fan.
And just to clear this up, do I have individual controls on my window unit? Like, I can specify the heat level in my unit individually? That's
right. So I mentioned two main components in that unit. There's the fan and the coil, but the third component is a control valve. So that's a valve that opens and closes to either start or stop the flow through the coil. So each room will have its own thermostat. A wireless thermostat will be on the wall. We do wireless so that, again, the idea is to be non-invasive. You don't want to run wires through a space. So a wireless thermostat on the wall that will tell two things to that unit. It'll tell the valve to open or close, telling it to, if it needs water or doesn't need water, and it will control the fan speed. So, the units are sized for the peak load, but most of the time you're not at peak load. So to your point about being quiet, if you don't need to run the fan at full speed, you can save a little bit of energy and make the unit even more quiet by slowing the fan down.
Right. So I'm not messing with the unit itself. The only way I interact with it basically is setting my thermometer where I want it.
That's right.
Is the idea that one of these units in one window of one room is going to heat and cool the entire apartment? Or is the idea that each room with a window to the outside is going to have one of these units?
The latter. So basically every room needs at least one of these. So most rooms will need one of them at the window, and it will serve that room. But, if it's a very big room that has multiple windows, you might need 2 units, for example.
Got it. And I'm guessing these window units, I mean, the way you describe them, they sound quite simple. I'm guessing they're relatively cheap. Like it's not a big problem to have a bunch of them, to have them on every window.
Yes. All of the parts that are going into this unit are really commodity pieces within the HVAC world that none of them are expensive. So this is a unit we developed ourselves because what's unique about the unit is really the form factor. So it's creating a unit that can sit within that 6-inch cavity that's narrow enough to fit in there. And not only that, but once it's sitting in there, the only way you can access that unit is through that top grill that you described.
Right.
And so you have to kind of arrange all the components in there so that all the maintenance, if you need to replace a valve, if you need to replace a fan, everything is accessible through that top grill. And even if you need to replace a unit, you have to be able to kind of disconnect the unit from the piping and ductwork, slide the unit out, and drop a new unit in. So it's a simple unit, but the form factor of it is unique.
And so it can be replaced with relatively little disruption. Then you just sort of like unplug the old one and plug a new one in, more or less.
Yep.
Very cool. One other interesting aspect of this is the space itself, the cavity space between the original facade of the building and the new facade you've hung on. One of the questions that popped up in my head, which you answered in one of your videos, is I'm thinking this space between the old facade and the new facade is effectively outside. So is it not going to get cold in the winter, for instance, and freeze all that water that's going through all those pipes? But then it turns out that this space is conditioned. So talk a little bit about how you're thinking about that cavity space and what you're using it for, because it comes in sort of handy in a couple of different ways.
So when we put this new facade on the building, this new outer shell, you can basically think of that as the building's new thermal barrier.
Right.
So anything that's inside of that shell is essentially indoors. Now, the tricky thing is when you overclad a building, what you tend to do is you run the risk of trapping moisture between the old facade and the new facade, because you're creating this airtight, watertight, enclosure.
And you're moving hot and cold water too, which seems like an invitation to condensation.
Exactly. So that's actually been a big issue with these type of overclad retrofits. You mentioned in your introduction that these kind of overclads kind of started in the Netherlands, became more popular in Europe. But this issue of trapping moisture and condensation becomes more of an issue when you get into colder climates.
Yeah.
So if all you do is overclad the building, you could run some real risks there with moisture in that cavity. So the way we get around that is by actually conditioning that cavity and specifically dehumidifying it. And the way we do it is conveniently we're delivering dehumidified ventilation there to each apartment.
Through the ducts.
So we already have that distribution through the ducts that are already sitting in the facade. So essentially what we do is we say, hey, let's just take a little bit of air off that ductwork and let's supply it directly into the facade, into that cavity. And so we're effectively dehumidifying that cavity. And it really only takes a very small amount of air to do that, because it's not, the space itself is not a large volume. And it's not like you have moisture loads like constantly pushing moisture into that space. So really just a small amount of dehumidified ventilation air can keep that space nice and dry.
So that's warm, dehumidified air basically circulating in that cavity, keeping it dry.
I would say it's tempered air. It's probably around 60 degrees. I mean, it depends on the season. It depends how you want to operate your building. But it'll probably be in the 60 to 70 degree range, the air that you're circulating.
Talk a little bit about how you're making use of thermal storage, which I found fascinating. Like the main heating of the indoor spaces is through this forced air, through this unit, but then there's also this supplement. Talk a little bit about that.
Yeah, so like you said, this is a pretty interesting aspect of what we're doing. So I just talked about dehumidifying that cavity, and kind of tempering it. But we then take it a step further, where we can actually heat the cavity. So we have, hot water running through the facade in the wintertime, and we can put a small heat transfer element using that hot water to actually heat the cavity itself. And so what that does is it creates this really interesting condition. So we have this cavity. On one side is this super insulated new facade. On the other side is this old uninsulated masonry wall. So the heat in that cavity is going to conduct through the uninsulated side. And it's essentially going to warm up that wall.
Right. The masonry is just going to absorb some of the heat.
Exactly. And we're not talking about it getting very hot. We're talking about the temperature in that cavity maybe being 80 degrees, 85 degrees, and then that wall maybe is warming up to 75 degrees, which, the typical set point in wintertime for a space is around 70 degrees. So we're just talking about getting that wall a few degrees warmer than the air temperature in the space. But that's enough for that heat to essentially radiate from that wall into the space. So you may be familiar with radiant floor heating.
Yeah.
So this essentially becomes radiant wall heating. So it's a very comfortable, very efficient way to heat the space.
Yeah, because this is the phenomenon. I forget what the name for it is, but like even if the air inside is warm, if the surfaces you're near are cold, you're sort of getting radiant, you're like losing heat that way. So warming the walls is actually not a small thing, comfort-wise.
Yeah. What you're describing, what it means is that, say, I have a traditional heating system in my room. I need it to be 72 degrees to be comfortable. And that might be because my window and my wall are cold. So even though the space is 72, I have those cold surfaces affecting my comfort. If all of a sudden you heat that wall, so now that wall's not cold, now that wall is actually warm, and you have a super efficient window, like a triple pane window that's not really getting cold, now because I don't have those cold surfaces, instead of needing 72 degrees to be warm, I can have the room at 70 and feel just as warm, or 68 and feel just as warm. So you're able to keep your space temperature lower, but feel the same comfort. But you mentioned thermal storage. And so where it gets really interesting is once you've heated up that wall, that's a massive masonry wall.
Yeah.
It has a lot of thermal mass. So you're actually storing the heat in that wall. So if you think of an example where you want to do demand response, which is, the grid is seeing a peak, it's a really cold winter night. The grid, is experiencing a peak and the utility wants people to curtail their demand, just as an example. And, utilities pay people to do this. This becomes very simple for the building now. All they have to do is turn the system off, and the heat that's in that wall will just continue radiating into the space and continue heating the space. And again, going back to the super insulated building, bringing the loads way down, just that little bit of heat can actually keep the space comfortable for a long time because the loads are so low.
That raises a question that I had about electricity, because you have this super insulated shell, so ventilation is super important, and the ventilation is being achieved by an electric heat pump or a fan. What happens if the electricity goes out? Do you not get very sort of clammy, oppressive air pretty quickly once the ventilation stops? Like what happens in the event of a brownout or a blackout? Hey there, everybody. Don't worry, I'm not going to tell you about a new mattress or push a credit card on you. This isn't an ad. There are no ads on Volts. It is supported entirely by listeners like you. If you'll indulge me for a second, I'd like to ask for your support. I started Volts because we're all surrounded by depressing news about climate change and misinformation about clean energy, and it's never been more important to share the stories of the real people on the ground doing the real work of transition, and all the ingenuity and courage and public spirit they are bringing to it. People are hungry to hear these stories, to learn from and find inspiration in them. I've heard from people who change majors or careers after hearing episodes of Volts, people using it in classrooms and community groups, even state legislators who have passed bills inspired by specific episodes. Sharing these stories matters. It makes a difference. If you have found value in it and want to help me continue doing it, I hope you will join the community of paid subscribers at volts.wtf. It's about the cost of a cup of coffee a month. If you don't like subscriptions, you can make a one-time contribution, leave a review on Apple or Spotify, or just tell a friend about Volts. I am grateful for any and all support. If you're already a paid subscriber, thank you. And now, back to the show. Like, what happens in the event of a brownout or a blackout?
Yeah, well, I mean, that's a very good question. As you said, if everything just turns off thermally, you'll probably be fine.
Right.
But your ventilation is going to turn off as well.
Right.
You can open your window. You always have operable windows as kind of a last resort if the air is really getting stale and you need to do something. But that's where, again, going back to the fact that, every building's unique. Every project, will have different requirements. If that's a concern, then I would say the main way to deal with that is to have backup power, backup, generators, whether it's batteries or whatever kind of backup it is.
Yeah, it'd be good to be on a little microgrid or something.
Yeah. And it depends how long, if the power's off for a couple of hours, it's probably not a huge issue. But if we're talking about days, then I'd say this one can be concerning.
The one piece we haven't really talked about is the facade itself, the facade panels. I'm guessing that different building owners will want different facades. Like, are you making the facades, or are these like a off-the-shelf product that you can just buy and add your stuff to? Or do you have to make sort of bespoke facade panels?
So it's kind of a little bit of both. We are not making our own facades. The idea is, as you said, different people are going to want different things, whether it's the aesthetic or particular materials or certain levels of efficiency. People are going to have different desires for their individual buildings. And so our intent is to make the system very flexible, to be able to work with, lots of different facade options. There's no reason you couldn't do it with all different materials, depending on what the owner wants. Of course, you have some limitations, like you can't use super heavy stone. If you're hanging this on the side of an existing structure, you don't want it to be too heavy. You want it to be lightweight. Obviously, you want it to be affordable. But it is generally very flexible. Kind of our company philosophy in general is that we're really specializing in developing this innovative HVAC system that kind of unlocks, this kind of potential to do these types of retrofits. But that's really where our specialty lies. Our specialty is not as a facade company. My background is as an HVAC engineer. Right. I'm not an expert, in facades, although I'm certainly learning a lot about it through this process. But so our strategy is to work with existing facade manufacturers to develop facades that will work for us. And so there are existing products on the market to do overclads, and essentially those same products will work with our system. There's a little bit of kind of integration work that needs to happen, like maybe some minor modifications to the facade system, some modifications to the way it's anchored, or things that need to be done to create that cavity. But in general, it is through partnerships with facade manufacturers that will kind of bring this whole system to the market. Like,
the facade itself is not that mechanically complex, right? I mean, it's just kind of like plywood with some material on the outside, right? I mean, these don't strike me as like a ton of variation possible, other than like the look of it aesthetically.
Yeah, I mean, my initial thought was the same, although now that, we're getting into nitty-gritty details of, developing these systems with a few different manufacturers, they actually can be pretty complex. They're not that complicated in the sense that, there's no moving parts.
Right.
It's just a insulated material and a structural material to give it rigidity. And you need, some degree of fire resistive element to it, so, it can't spread fire. But the complexity is more around the installation process.
Yeah.
It's around the anchoring system. Like, how do you design these anchors to attach to the existing structure? And then how do you design those anchors so that you can easily hang the facade panel to them? And then how do you actually seal between the facade panels?
Yeah, that's what I was going to ask. Like, what does it look like? How do you create an airtight seal between these two big chunks that you're, 100 feet up in the air hanging on the side of a building?
Yeah. So facades, panelized facades are extremely common in new construction, right? You see a lot of, tall buildings or maybe even not tall buildings going up where you see people lifting facade panels into place or, even from the interior, putting facade panels on the exterior of the building. So the whole concept of, sealing between panels and how that gets done is, pretty standard. And it falls into two categories. You have what's called dry seals or wet seals. So a dry seal is where you have some kind of, gasket material where the two panels kind of come together and the gaskets form a seal. And that's good because there's not that much labor involved. It's really just putting the two pieces together. The alternative is a wet seal system where you put the two panels next to each other and then you have, a wet like silicone kind of seal that has to be installed between them. That's a bit more labor intensive, but a bit simpler. So there's pros and cons to either one, and we can potentially, do it either way.
Right. So if I clad my building in one of these systems with the facade airtight and the ventilation system that you describe, am I going to meet Passive House standards? I mean, it sounds like that's basically what Passive House is, right? It's like an airtight seal and good ventilation. Are you going to meet that standard?
Yeah, so I would say potentially. And the only reason I don't say yes, definitely, is because I'm not 100% sure, but I believe essentially to be Passive House, ultimately the metric is what is your energy use. So they have what's called the EUI, the energy use intensity. And to meet Passive House standard, you basically have to meet a certain energy use intensity from your heating and cooling system. Now, there's all sorts of ways to do that. All the principles of Passive House with eliminating thermal bridges and high performance windows and all these things. But ultimately, I think the question of is your building achieving Passive House or not, I think comes down to whether or not you're hitting that energy metric. And so the only reason I say maybe for us and not definitely is because I wouldn't want to set a somewhat arbitrary metric as, a necessity. Let's just pick random number. Let's say the Passive House heating EUI, let's say it's 3 kVT per square foot per year. I don't know if that's exactly what it is, but something like that. If we end up, designing a project and, choosing the materials that make sense for us based on, budget constraints and, whatever, and we end up with a 3.3 EUI for heating, I'd say that's good enough. We don't necessarily need to, hold ourselves to the Passive House as a requirement.
So let's talk about what buildings can do this then. What are the restrictions? Like one thing that occurred to me, and I saw you say this in a video too, it seems obvious in retrospect. Obviously, you can't do one of these big all glass buildings, right? Because you got these panels that have stuff in them, so they have to be opaque, right? So at the very least, you can't do all glass. Are there other sort of restrictions on the type of building facade this works on?
I'd answer this in two ways. If we kind of step back and look at our kind of longer term vision, we imagine just this kind of general concept of integrating the HVAC into the facade of a building. We see ways that can be done for lots of different building types with lots of different physical characteristics. Even in all glass building, if the building owner is okay with blocking off a portion of that glass in order to have, that duct and pipe distribution that's, kind of blocking it, then it's certainly doable. And, for an all glass building that wants to be energy efficient, maybe that's a smart thing to do.
Yeah.
Maybe you don't need to be an all glass building anymore.
Yeah.
So, that's one example. But even looking at other building types, like office buildings, for example, there's no reason that this kind of approach couldn't work for an office building, but it's just different.
Yeah, why are you focusing on multifamily? There are some reasons you're not starting with offices or commercial buildings.
Right. So multifamily is really ideal for, I guess, a couple of reasons. One is that they tend not to have deep floor plates. So we're talking about conditioning a building essentially from the exterior, from the perimeter of the building. So if you have a space that's, 50 feet deep, then that's a lot harder to do. But with multifamily buildings, you typically don't have deep spaces like that. You're typically not allowed to by code. Every space has to be within a certain distance of an operable window for light and air. So from that perspective, multifamily works really well. The other perspective is that multifamily buildings tend to have small internal loads. So, if you look at the cooling load of a building, you have the envelope, where you have your exterior loads, like the sun coming in and, it's really hot outside and that's conducting through the wall. So you have your perimeter loads of the building. And when you super insulate a building, you can bring those loads way down. But then you still have your internal loads in the space. Things like lighting or people or, your computer and your TV that's plugged in.
These are not commercial machines in the case of a multifamily building.
Exactly.
Just ordinary appliances.
Exactly. So your internal gains, heat gains in a multifamily building are relatively low. So once you super insulate the facade, your overall loads can be very, very low. But to your point, with an office building, you can have, tons of computers and, commercial density of lighting and lots of people packed into a space. And so your internal gains are still much higher. Even though you're super insulating the facade, you still have all these internal gains. So your loads in general are higher. And then the other thing is you need a lot more ventilation air for a space like that. If you have 30 people in a section of an office, they need a lot more ventilation air than, just a living room does. And so when we're talking about squeezing ducts into a narrow facade cavity, it's a lot harder to do that if you need, much higher volumes of ventilation air.
Yeah.
So there are approaches you can take where, and we're not doing this now, but we foresee in the future where you could do this exterior approach essentially just to handle the perimeter loads of an office building, but then still keep your kind of existing interior systems to handle those internal gains. So there's ways to make it work, but multifamily really is the most straightforward, for taking this kind of approach.
I'm just curious, like from a resident's perspective, if a building owner says, yeah, I want to do this, does the resident ever need to move out? Like you do have to pop the window out. Can you do that from the outside? Like, can you do everything from the outside? Can the residents just chill inside and not worry about this?
I would say yes, the residents can chill inside, but not all of the work is happening from the exterior. And that's, to your point, it's really the window. So the way this will happen is the new facade panel will get installed on the exterior and, all the HVAC distribution installed on the exterior. But then the window, the existing window, needs to be removed from the interior. So after all that stuff gets installed on the exterior, a contractor will have to come in, remove the existing window.
Oh, so the whole outer facade is put in place and then the original windows are removed.
Correct. So the contractor removes the original window and then you end up with this kind of unfinished window opening that they have to kind of, do some finishing work to close it out, to make that whole new windowsill look nice and everything. So the residents definitely don't have to move out. And even when you do retrofits, even when a resident doesn't have to move out, sometimes it's still very invasive, just to have the contractor doing work throughout the apartment. Maybe you have to move furniture around, maybe you have like a big bookshelf here, but the contractor needs to run a pipe across there. So you have to, move your bookshelf out of the way. And, so it can still be pretty invasive, even if you're not moving out. But with our approach, fortunately, the only access that's needed is at the window. So you don't have to move any furniture around. It's not really a major disruption. And the idea is that it's a small enough amount of work that it could be done in less than a day. So, for the resident, you're going to have one day where, contractor's going to come in, do some work at the window, and then be done.
Sort of the big obvious question we haven't addressed yet is cost. Just when I think about a big building, an entirely new facade full of HVAC equipment for a big building, that's just a lot of material. It's just a lot of stuff. So this sounds on its surface expensive. So try to give us some sense of how this fits into the retrofit landscape. What's the pitch to a building owner?
The two biggest barriers to electrification, I mentioned one is the invasive nature of the work.
Yeah.
But number two is definitely the cost. You can't have a discussion about technology or, decarbonization or anything without talking about cost, because ultimately that's going to be the decider for whether or not these projects actually happen. Now, to your point, putting a whole new facade on the building and putting a whole new, HVAC system with distribution is obviously not cheap. But the way we look at it, what we think is the right way to look at it, is to not just focus on the installation cost, but it's about the work being cost effective. which really has two sides to the equation. There's the installation cost, but then there's the operating costs after you do the installation.
It's just classic decarbonization story. Big upfront investment, big savings over the long term.
Exactly. And in this case, it's not just about energy savings. So, obviously, if you super insulate the building, install this really efficient HVAC system, you will have significant energy savings, which is important.
Mm-hmm.
If you just install heat pumps in a building, you probably don't have much energy savings because electricity is generally more expensive than gas. But when you super insulate the building and bring the loads way down, now you will have significant energy savings, even though you're switching to electricity. But it goes actually well beyond just your energy savings, because you're actually going to see a lot of maintenance savings as well. And the biggest component of that is actually the facade. So when you talk about these older masonry multifamily buildings, they actually spend a lot of money inspecting and repairing those masonry facades.
Oh, yeah, right. Interesting. And this will protect that from the weather, I guess, obviously.
Yeah, exactly. So your masonry is essentially indoors now. You never have to look at it again. And you have this new, very low maintenance, very durable facade material on the exterior of your building. So you're saving a lot of money on your facade maintenance.
And the HVAC is relatively low maintenance too. I mean, compared to, I'm guessing, like an old boiler and radiator system.
Exactly. Yeah. I mean, if you think of, an old big boiler system with steam piping, all over the building, and steam traps, leaking, and just people complaining about too much heat, lack of heat, and, someone needs to go and just
opening their windows with their radiators on. Classic New York picture.
Exactly. So the point here is that you have this upfront cost, which is substantial. You also have cost savings, operating cost savings, which is substantial. And so the way to really make it work from our perspective is to have financing.
I swear I have this same exact conversation about every technology. It all comes down to the financing.
Exactly. Because if you can finance it so that the owner doesn't actually have to pay the money, up front, then that installation cost doesn't become an issue. And that's when, the cost savings, if you have significant cost savings, and you can use those cost savings to pay the loan payment. I mean, again, very classic example, whether it's with solar or whatever, this is very common. It's just that with buildings, with deep energy retrofits of buildings, it's always been very hard to get that equation to actually work.
Right. Well, this is the inevitable next step in this conversation, which is your technology comfortable enough, familiar enough to banks that they will finance it?
Right. So that's a big question. So just to back up for a moment in terms of where we are with our technology development, we haven't installed the system yet. We have our first pilot project on a building in Syracuse that will start construction in the second half of next year. So the question of, are banks familiar and comfortable with it? No one's familiar and comfortable with it yet.
Not even
that's
you.
That's part of the challenge of being innovative and trying something new, especially, in the construction industry, which is a very risk averse, kind of industry. But to be honest, we're thrilled just to have this pilot project lined up, because that is a huge challenge. That's the biggest challenge in itself.
You're going to need a few people to step up and sort of make the big initial investment, just to get a first of a kind thing that people can look at.
Right. It's unlikely to be just, your standard bank loan, doing it for these early projects. It's going to be some kind of, subsidized loan program, whether it's something federally subsidized, like from the IRA or...
Are there IRA? I mean, I'm not sure exactly where you would classify this exactly, but is there money in the IRA somewhere for this kind of thing?
There is. It's complicated, and I'm not expert on all the details, of the IRA and where we can kind of take advantage of it. But there definitely is money for decarbonizing buildings, and because we're focused on old multifamily buildings, well, a lot of those buildings are affordable housing. Yeah,
I was going to say there's a real environmental justice angle here that we haven't even really touched on yet. But another good reason to start with multifamily buildings rather than offices is that there's a lot of very uncomfortable, low income people living in these buildings.
Exactly. And, like you said, environmental justice, going back to the public health issue and all of that. So that is, I think, where the opportunity is right now. And that's where, like you said, where the need is, kind of most urgent right now.
You mentioned this in passing earlier, but I think it's a really intriguing piece of all this, which is that, a lot of these buildings, like just take New York City for an example, are on grids that are quite congested and overburdened. And so you dramatically reducing total load and also spikes, right? Like evening out those spikes over time is a great help to the grid in these places. So I just wonder, have you talked to utilities, and is there any prospect of utilities helping a little bit with the financing?
There's definitely a prospect of it. And like you said, it's definitely in their interest. I don't have anything specific at the moment where we have specific support from utilities on any specific projects, but it's definitely, for the reasons you said, it's in alignment with their goals of, controlling the grid, not overloading the grid. And, back to another earlier point about district thermal systems, that's a really interesting area for utilities as well, to operate these district thermal networks. And, in a sense, what we're doing really unlocks a lot of potential there, because I think with multifamily buildings, the biggest challenge with district thermal networks is, you can bring that thermal energy to the building, but then how do you distribute it to each apartment? And so that's kind of the piece that we help with. We've had discussions, nothing concrete, but we expect that there's going to be a lot of interest from utilities from that perspective as well.
And especially in cold weather climates, because of course, one of the big vexing problems with electrification is electrifying heat in cold weather climates is, all things being equal, just an enormous new load on grids that don't necessarily have a way to meet it. So dramatically reducing your energy demand while you're electrifying is so crucial in those climates.
Yep, exactly. It's like a double whammy in cold climates, because you have a higher heating load just because it's so cold out, but also the heat pumps operate less efficiently and have less capacity. So it's like an exponential kind of challenge that the colder it gets much, much harder to electrify.
So a couple of final questions. One is just sort of what do you envision for your company? You're trying to show that this whole thing can work. Do you envision being the company that a building owner calls and you go do this? Or are you going to license this to construction companies that make facades? Or what's the sort of business model you envision?
Yeah, could potentially evolve in different ways. But going back to an earlier point we were discussing, we really see our expertise, the real value we bring is in this kind of HVAC technology and developing this new kind of HVAC approach. And, we don't necessarily feel a need to be handling the entire project ourselves. I mean, me personally, like we said in the beginning, I'm a huge nerd. I'm a huge geek. I'd be totally happy just sitting there working on the technology, making the technology better and better, while other people worry about, managing
business models,
projects and
talking to utilities.
Right, exactly. So right now, our model is that we're going to work with partners who will actually implement these retrofits. So right now we have a great partner called Cycle Retrotech. They are a retrofit solution provider, basically doing deep energy retrofits, and they have experience with overclads. And so they're essentially going to manage these projects.
They must be geeked about this, right? I mean, this is such a perfect complement to their product, right? It's just makes so much sense.
Yeah, I'm really happy with that model, with that approach. They'll manage the project. So the idea is that these will be kind of turnkey design build projects. These can't be complex construction projects where the owner has to manage all different consultants and then send these projects out to bid, and who knows how the bids are going to come back. These need to be design build turnkey projects where someone like Cycle Retrotech is going to go to the building owner and say, I'm going to retrofit your building for this price. And then they bring the whole team, they bring the whole package. We talk about financing, they'll bring the financing, make it as simple as possible for the building owner. And, if we just have our tiny role of just providing these certain HVAC components, these terminal units, and maybe having a licensing fee that goes along with it, then that works for us.
You just want to do the engineering. I completely sympathize with that. You also mentioned, actually, in passing in some of your materials, that you also think that this system would be preferable for new buildings, which I found quite interesting. Like, the advantages for retrofits are obvious to me, but you think even in a brand new building, integrating the HVAC into the building facade is the way to go, even for new build?
Yeah, I do. I think it's almost just as interesting and just as exciting to think about what it could mean for new construction. We talk about the urgency of decarbonization of our existing buildings, but we also have an urgent problem with housing and affordable housing, and we need to build a lot more housing. In this country and around the world, actually. We need to build a lot more housing. We need it to be affordable. We need it to be efficient and healthy, and all these things. So if you think about building a new building, a new multifamily building, and you think about the HVAC work that happens in that building, you think about the contractor in there installing ductwork for the exhaust systems and piping, whatever kind of heating and cooling system it is, and all this work that happens in the building, which is pretty labor intensive. And now think, instead, that whole structure gets built, the mechanical contractor is not in there doing anything, but instead all of the ductwork and piping is all prefabricated onto the facade panel. And then you literally just take that prefabricated panel, and these can be big panels, these can be like 30-foot long panels, serving the whole apartment. You just take that panel, mount it to the side of the building, and then the work from the inside is just kind of connecting the ducts and the pipes between the panels.
Right, hook it up like Legos. You wouldn't even necessarily need, like plumbers per se, like skilled labor. It sounds like something that like anybody could do, basically, like stacking Legos, more or less.
Yeah. So for the HVAC, yes, of course you still have, the sanitary piping, all the plumbing, which probably won't be part of our system.
Yeah, right.
But from the HVAC side of things, all of that, the work is essentially moving into a factory, which is great for workers. I mean, if I'm a worker, I'd much rather be, in a conditioned factory on a stable floor working rather than on a, construction site. So I think it's better for workers, but it also makes it more efficient. And, at the end of the day, again, it all comes down to cost. We need to build a lot of housing. We need it to be affordable, and this can really reduce the cost.
This is like a custom-built segue to my final question then, which was about, what I like to ask anybody who's got a new technology they're working on, which is, how do you see costs coming down over the long term? What are the sort of channels through which you're going to reduce costs? Because in a sense, like a lot of mechanically, there's not a lot that's super complicated here. These are not, I mean, that's sort of one of the benefits of the whole thing. These are pretty simple pieces you're assembling here. So, it's not like small fans are going to dramatically reduce in price over the course of the next. So where do you see opportunities to reduce costs for the whole thing?
That's a great question.
And what might help, actually? What might help policy-wise, if I can tack that on too?
Yeah. The biggest opportunity to reduce cost. So like you said, the materials themselves, they are what they are, but really the biggest opportunity is in the labor cost. Mm-hmm. So making the installation process more efficient.
Yeah.
So the more that we can automate. So let's think about what one of these installations will look like. You essentially scan the exterior of an existing building. You can automate much of that. You take that digital information and send it to the facade manufacturer, who can now fabricate their panels to perfectly match, the existing building physical conditions. And again, much of that can be automated. Then you have an anchoring system that we need to make it, simple to install as possible, installing these anchors on the building, and then, having your lift or crane or whatever that's bringing the panels onto the building. We can make that process very efficient and taking a lot of labor out of the equation and taking the labor, not just taking it out, but moving it to the factory where it's more efficient.
Yes, as all Volts listeners know, anything you can do that's modular and replicable and doable in a factory is going to lend itself to a declining cost curve.
Yeah, exactly. So if you think about it, if you're doing retrofit work in the apartment, there's no way to take that to the factory.
Yeah.
But when you're doing it as part of an exterior panel, now you can take it to the factory and then just bring that panel and slap it on the side of the building. One of the biggest chunks is just improving the processes so that we can make the labor component as efficient as possible. And then the other piece is just economies of scale.
Yeah.
When we're doing one building here, one building there, then the cost of those facade panels are going to be a lot more than if we're doing 100 buildings, 1,000 buildings. So I think economies of scale are the other area, where we'll get cost savings, which again is something you get with, a modular offsite kind of approach that you don't necessarily get, with traditional construction. So I think those are the two main things. You asked about policy. To me, the hardest part of reducing that cost is kind of getting to that economy of scale, because if it's
another familiar
chicken and
story
egg problem, if it's expensive now, then how are you going to get the volumes up to where you can reduce the cost? So to me, that's where policy can come in to kind of help support the earlier projects, to help support manufacturers to scale up their capacity so that we can actually get to those economies of scale. Because I think ultimately, organically, we could potentially slowly get to economies of scale, but, we don't have the luxury of time. We need this to happen, today.
In New York City, that's where you're sort of...
Yep, we're based in Queens, New York.
New York in particular has laws and regulations about rapid decarbonization of large buildings. Yep. Are there New York State subsidies in particular available or assistance available in New York? So
in New York State, we have NYSERDA, the New York State Energy Research and Development Authority, I think something like that. So NYSERDA, that state agency, they're providing a lot of support to kind of get this market going. And we've gotten significant support from them, and they're actually helping to support the pilot project that we're planning in Syracuse. So I think they recognize the need, and they are trying to help support that market and get that market going. We have laws in New York City, essentially requiring buildings to decarbonize.
Yeah, very aggressive.
Right. But the way those laws work is essentially buildings get fined, if they exceed emissions limits. But unfortunately, right now and for the foreseeable future, as much as building owners don't like paying fines, paying the fine is probably easier and cheaper than doing the retrofit. So, a lot of them will probably just be upset and pay the fine, but it won't, achieve the desired goal. Yeah. So certainly fines like that are not enough to push the market where it needs to go.
Yeah. It just occurs to me, this is a very random question, but I forgot to ask it earlier. It occurs to me that if you have a building that is newly clad on the outside with a network of pipes carrying water, is that fire prevention? Like, have you thought about that angle at all? Like, is there a fire angle to this?
Well, I like the way you think. I mean, it certainly could be. Fire is a big thing, actually. That's actually one of the big kind of issues we have to deal with is, how do we ensure that this is going to be safe from a fire code perspective? And I think that's a really cool idea. How can we kind of leverage that water in there to help, with the fire safety? I hope you don't mind if I use that.
No, please. I'd love to have some small geeky contribution to this whole to this whole thing. Well, David, this has been absolutely fascinating. Such a geeky pleasure. This is a real fun work you're doing. I hope it takes off. I mean, it seems like something like this is how I always feel when I hear about a cool new tech idea. Something like this seems inevitable to me on some time scale. Just like working from the outside rather than having to schlep around inside is such a big thing. Somebody's going to make it work. Thank you so much for your work and for coming on today.
Yeah, thank you so much. Really enjoyed the conversation.
Thank you for listening to Volts. It takes a village to make this podcast work. Shout out especially to my super producer, Kyle McDonald, who makes my guests and I sound smart every week. and it is all supported entirely by listeners like you. So if you value conversations like this, please consider joining our community of paid subscribers at volts.wtf, or leaving a nice review, or telling a friend about Volts, or all three. Thanks so much, and I'll see you next time.